is Math 139, Section 3.9, Part A. We're going to begin looking at properties of logarithms. There are three major properties that we're going to be looking at in this section. And the first one is called the power property. It looks like this. The power property of logarithms. The logarithm base b of x to the p power is equal to p times the logarithm base b of x. Notice what happened here. The power on x became the multiplier on the log in the simplified form using this power property. Now, it may seem a little weird that we can do that, and I would agree with you. It's not an obvious thing. So let's just try it out and just look at with our calculator and see that it seems to work, at least in one particular case. I'm going to start by taking the logarithm of 4 cubed. And notice I get 1.80618 approximately. Now, if I follow this power property of logarithms, the exponent, the 3, can be brought down in front as a multiplier on the log of 4. And 3 times the log of 4 is supposed to be the same thing. Let's check it out. And there we go. You can notice that right all the way down to the last decimal place that the calculator shows, we do indeed get the exact same answer. So yes, we did. Now I know that's only one example. You could actually try many, many of these if you wanted to, and you should see that this power property works every single time. So if I have a base raised to a power inside a logarithm, I can take that exponent and I can bring that down in front as a multiplier of the logarithm. Let's practice that a little bit. Let's go ahead and use our power property to rewrite these expressions. Number 1, the log base 7 of x to the 5th. I'm going to use the power property, and I'm going to take that 5, and I'm going to say I can bring that down as a multiplier. 5 times the log base 7 of x. Now, in order to use this property, we must have this exact form. It must be something raised to a power. Notice we don't have that exact form in number 2. We have 1 over something raised to a power. In order to use our power property here, we're going to have to rewrite this. 1 over x cubed is the same as x to the negative 3rd, right? When I bring my x cubed across the fraction bar, it changes signs. Now I've got it in the form that I need it. I've got my x being raised to a power, and according to the power property, I can move that power down in front as a multiplier. Compare numbers 3 and 4 here. Here the entire 4x is squared. Here just the x is squared. This one is already in the form where I can use my power property. This exponent 2 applies to the entire argument for x, and so I can say the power property tells me I can bring that 2 down in front as a multiplier. Here, I can't use the power property in this form. That 2 does not apply to the entire argument, and therefore the power property does not apply. In fact, there's something I can do to rewrite this so that I can use the power property. I recognize that argument 4x squared as a perfect square. So I could first rewrite this as the log of 2x all squared. And now the power property does apply in this form. Now I can say this exponent applies to the entire argument, and so I can bring it down in front as the multiplier. So there's our power property. In fact, the power property can be used to solve equations that contain exponential functions. We already looked in section 3.8 at one method of solving these equations, but we're now going to see a second method based on the power property. So this is method 2. It's called the common log method. And we're going to always start, just like we did before, by isolating our exponential. We have to get it by itself. This time, instead of applying the logarithm for the specific base in the problem, we're going to apply a logarithm always base 10 to both sides of our equation. And we're going to use our new power property to simplify. Once we've done that, we should be able to solve for x. So here we go. These are the same exact problems that you saw in section 3.8. And in fact, I would encourage you to check back in your notes in section 3.8 and verify that the answers we get here are the same ones that you saw there. In number 1, our exponential, 8 to the x, is already isolated. So I'm going to go right to the idea of let's do the logarithm base 10 on both sides. Here's that power property. That exponent of x can be brought down in front as a multiplier. And we've got x times the logarithm of 8 equals, everybody remember what the log base 10 of 100 is? 100 is 10 squared, right? So the log of 100 is actually 2. Of course, if you don't remember that, your calculator will certainly remind you. All right, to get x by itself, it looks like I just have to divide both sides by the log of 8. And so I'll do that. And it's about 2.215. It's really an approximation. I should use my approximately equal to. So this is an exact answer. And this, of course, as soon as we've gone to the rounded off decimal, is an approximation. In these problems, we're going to give both our exact answers, which will contain a logarithm as part of the answer, and then also an approximation, rounded to 3 decimals, just like we did. All right, let's try the next one. In the next problem, we do not have the exponential isolated to start with, so we're going to have to do that. We've got the 5 to the x is our exponential piece, and I want to get that alone on one side. So I will add 4. And then I'll divide by that multiplier of 3. And I get 5 to the x equals 9. Now we're in the situation where the exponential is isolated, and we're going to apply our new technique of taking the log base 10 on both sides. Here's our power property. That exponent of x can be brought down in front as a multiplier by the power property of logs. And this time I don't recognize either of those. Neither one of them simplifies to some nice number, so I'll just leave them in this form. To get x by itself, I have to divide by the log base 5. There's my exact answer right there. And I can get a decimal approximation for that. Log of 9. By the way, be sure you close your parentheses on the logarithm before you hit the divide sign. That's a common error that causes people to get incorrect answers, is not closing those parentheses. About 1.365. Again, I would encourage you to check back with what we got in 3.8 to verify that we're getting the same answer here. You'll be able to check the decimal approximations. All right, our last example of this process. My exponential is isolated in this equation, so I'm going to go ahead and go with the logs right away. The log of 15 equals the log of 4 raised to the 2x minus 5 power. This time, the entire 2x minus 5 is the exponent, so I'll have to bring that entire thing down in front as the multiplier when I apply my power property of logs. So I'll have the log base 15, and then I'm going to be very careful here. The entire 2x minus 5 is multiplying the log of 4. So notice that I kept it in parentheses, or put it in parentheses, when I brought that down as the multiplier. All right, my goal is to get x by itself, so a little bit more work to unravel this one. I'm going to go ahead and divide by the log of 4. And again, neither of those are particularly nice numbers as far as being the logarithm of something I recognize. So I'm just going to leave them in that exact form for now. And I'm going to start working at getting the x by itself. I'm going to add the 5, so I'm going to bring that over. And then I have to divide by 2. Dividing by 2 is the same as multiplying by a half. And it might actually look a little easier algebraically if I write it as times 1/2 this time. When I distribute the 1/2 then, I get the log of 15 divided by 2 times the log of 4 plus 1/2 times 5 would be 5 over 2. Of course, over here the 2's cancel and I just get x. So there's an exact answer. If I want a decimal approximation, I can put that into my calculator. Again, being careful to close those parentheses. Here again, watch out. I want the entire 2 log 4 in my denominator. And then add the 5/2. And I get about 3.477 if I round to 3 decimal places. Okay, so there's a second method of solving these equations. This one's really common. We haven't had log base keys other than base 10 on the calculators for very long, and so a lot of people actually use this method rather than the other one. You can check with your instructor and see if they prefer one over the other. Otherwise, you can pick the one that you like best.